Okay, so in this video, we're going to talk about potential energy. So far in this unit, we talked about work, which work is not a type of energy, but it's the way a force transfers energy to or from an object. And so really, the only energy we've talked about so far is kinetic energy, which is the energy of motion. And so in this video, we're going to talk about potential energy, and there's two main types of potential energy we're going to talk about. Now, potential energy is energy that is stored in an object dependent on the position of that object. And so when you think potential, it's like the potential for something to happen later on. And like I said, there's two main types of potential energy we're going to focus on. That's spring potential energy, which is also sometimes called elastic potential energy, and gravitational potential energy. And so I'm going to label for spring potential energy, I will do ES for spring potential energy. And again, some problems might call that elastic potential energy. That's the same thing. And then gravitational potential energy is going to be EG. Okay, and so we're going to start off by talking about spring potential energy. Even though really elastic potential energy is a more generic term, um, spring potential energy is the type of energy you have when you have like a spring or a rubber band or something stretchy like that, like a bungee cord or something like that. Gravitational potential energy, as we'll see later on, is energy stored because of height. Okay, but let's start off by talking about spring potential energy. Okay, so pause here, make sure you add this to your notes. Okay, so spring potential energy is energy that can be stored in a spring or a rubber band by either stretching it out or pushing it in from what's called its equilibrium position. Okay, so let's talk about what that equilibrium position means more carefully. So let's say here's a wall. Let's say you have a spring attached to the wall like this. Okay, and so let's say the spring is it's attached to the wall and it's just hanging there, it's not doing anything. Okay, this is its natural rest position right here. This is what we call the equilibrium position. This is what we call x equals 0. Now, I can take the spring and I can either stretch it out or I can push it in. Okay, either way is going to store spring potential energy inside the spring. Okay, but the natural resting position of the spring is what's called the equilibrium position. Okay, now, in order to store potential energy, what I need to do is I need to displace the spring from its equilibrium position. Okay, and so let's say I take this end here and I literally like yank on the spring and I stretch it out from its equilibrium position. Okay, so now there is a separation, there is a distance of separation between equilibrium and the new position of the spring. And that is what we call x. Okay, and so the variable x is the distance from equilibrium that a spring has been displaced. Now, technically speaking, I guess it really should be displacement, not distance, but it almost doesn't matter because if you look at the spring potential energy equation, um, x is being squared in the equation, and so even if you had a negative displacement, when you square it, it becomes positive. Okay, so notice here, I wrote this as PES. I think I'm going to change that, though, to be just ES. Okay, so spring potential energy. All right, now let's talk about the equation for spring potential energy. So ES is the spring potential energy that is measured in joules. We talked about that before. And in order to calculate that, the equation is 1/2 times K times X squared. Now we've already talked about what X is. X is the displacement from equilibrium that a spring has been either pushed in or pulled out. K is what's called the spring constant. Okay, so K is a constant for a given spring. And basically what K measures is like how stiff a spring is. And so some springs are really stiff and some are really not stiff. And so for example, like a slinky, if you've ever played with a slinky, that would be an example of a low spring constant because a slinky is not really stiff. On the other hand, if you think like the spring inside like a mouse trap where you pull it back and then when you let it go, it snaps closed really quickly, that would be an example of a high spring constant. Okay, so K is basically a measure of how how stiff the spring is or how much energy you can store in the spring. Okay, basically how strong is the pull of the spring. Okay, so make sure you add that equation to your notes. Okay, and what you can see from the equation, by the way, is the bigger the value of K, the more energy you can store in the spring. The farther out you displacement from equilibrium, either pushing it in or pulling it out, the more energy you can store in the spring. Okay, and so here we can just see, if you take a spring, you can either compress it or you can stretch it, and either way, you're storing energy in that spring that can be used for stuff later on. Okay, and here is basically just showing you, this is the equilibrium position up here at the top, and whether you pull it out or push it in, you're still displacing it from equilibrium, and therefore storing spring potential energy in the spring. All right, so let's do some basic calculations. Okay, so example 1. It says a spring with a spring constant of K equals 20 newtons per meter. So the unit of spring constant is Newton per meter. We're not going to talk about why that is for right now, but it is newtons per meter. And it says it's displaced from equilibrium such that 200 joules of potential energy, and of course it's spring potential energy, is stored in the spring. If the displacement of it says the displacement of the string, it should say spring. If the displacement of the spring is now doubled, how much potential energy will be stored? So this is a proportional reasoning question. We've seen this question many times before at this point. And so basically what this is saying is, okay, so, it's 1/2 kx squared. What's going to happen if I double x, if the displacement of the spring is now double? So in other words, what is ES prime if I make that change? In other words, if I turn x into 2x. Now, at this point, you might be saying, well, what are you doing about that K value? And they give you 200 joules of potential energy. What about that? We'll come back to that in just a second. Okay, because after I read the question and recognized it as a proportional reasoning question, that changes how I approach it. So now I keep K the same, but I'm replacing x with 2x, and the whole thing has to be squared. Okay, 2 squared is 4, and so I get 1/2 times K times 4 times x squared, which reduces to 2kx squared. Now, it's really important that you compare this to the original. My new spring potential energy has a 2. My original had a 1/2, which means that my new spring potential energy is 4 times the original value. Okay, some people might just see the 2 and think, oh, it's, the answer is 2. But you have to compare the 2 to the original value of 1/2. 2 is 4 times bigger than 1/2. Okay, and now I'm done. I'm ready to answer the question because I'm actually told the original value for ES is 200 joules, and so the answer to the question is 400 joules. Now, this is not the only way I could have approached this problem. What I could have done is I could have just taken my equation for spring potential energy, plugged in the 200 joules, plugged in the K value, solved for X, then doubled the X value, taken that value and plugged it back into the equation. And I could have done that, but this was easier to do as a proportional reasoning question. Okay, so pause there if you need to look at that some more. Okay, example 2. So example 2 says a compressed spring does work on an object with an efficiency of 40%. Okay, so that means E is going to be 0.4. And in the process transfers 40 joules to the object. Now that does not mean that 40 joules was stored in the spring. That just means that 40 joules ended up inside the object. During this time, the compressed spring returns to its equilibrium position over a distance of 2 centimeters. Okay, so think about what that means. That means originally the spring was compressed. It goes back to equilibrium. It takes 2 centimeters to get back to equilibrium, meaning that this 2 centimeters was my x value. Okay, so x is 2 centimeters, but anytime you do a calculation, you have to make sure you're in SI units, and so I need to convert that into meters. So that's 0.02 meters. Okay, so let's think this through. First question says calculate how much potential energy was stored in the spring. 40 joules went into the object. That doesn't mean 40 joules was in the spring because there is only a 40% efficiency rating. Okay, so let's think about this. Efficiency is output over input. Whether you're talking about energy or power doesn't matter. We know E is 40%. That's 0.4. We know the output is 40 joules because that's what goes out of the spring and into the object. Okay, so how much energy was originally stored in the spring? If you do the math, you get 100 joules, which makes sense because, 40% of 100 is 40. Okay, so that is how much potential energy was stored in the spring to begin with. ES equals 100 joules. Now that we have that, we can answer the second question, calculate the spring constant for the spring. Okay, pause it here and try to do that on your own. Okay, so we have ES equals 1/2 kx squared. So we have 100 equals 1/2 times k times 0.02 squared. And so I'm just going to get my calculator. I'm going to multiply both sides by 2 to get rid of the half. And then 0.02, if you square that, 0.02 squared, you get 0.0004. And if you divide by both sides, you can get the value for k, which is, let me just plug that in, 500,000 newtons per meter. Okay, which is the answer to the question. So pause there if you need to look at that some more. Okay, example 3. So example 3 says a boy does 0.4 joules of work as he winds up the spring in his toy car. Assuming the spring constant of the car is 8,000 newtons per meter, calculate how far the boy has to twist the spring. All right, so this is partially a concept question. So we're given spring constant, we're given K. How far the boy has to twist the spring? How far is a question about distance or displacement? Okay, so we're asked about x. By the way, some of you might have played with one of these toy cars when you were younger, where you twist the little spring and you basically wind up the car, and then you put it down on the ground and then it goes. Okay, so the way those cars work is using spring potential energy. So what do we do with this? Okay, so this is partially a concept question. Remember, work is the transfer of energy. And so when it says the boy does 0.4 joules of work, that means he is adding 0.4 joules of energy to the spring. Now, then you have to ask the question, what type of energy does the spring gain as a result of that work? Well, clearly it gains spring potential energy. So he does work in the spring, he adds energy from his body into the toy car, and now the spring potential energy is 0.4 joules. So when you're doing problems involving work, you have to think, okay, so this is how much energy I'm adding or removing from the object, but where is that energy actually going? What type of energy is showing up? Um, and in this case, it's spring potential energy. Okay, so as long as you understand that simple concept, you should be able to answer the rest of this question on your own. Okay, so try to answer this question now. Okay, so you should get 0.4 equals 1/2 times 8,000 times x squared. That should give you 0.4 equals 4,000 x squared. Divide both sides by 4,000 and take the square root. Okay, so I'm going to do 0.4 divided by 4,000, square root in my calculator, and I get x equals 0.01 meters. Okay, so that is example 3. All right, so that is it for spring potential energy. Very simple concept. Um, we're going to go ahead and stop here, and then uh, next we're going to talk about gravitational potential energy, and then the last part of this unit is going to be putting all of these concepts together and talking about mechanical energy and the conservation of mechanical energy. All right, so as always, please let me know if you have any questions, and I'll see you guys in the next video.